Good morning, everyone, and welcome back to Foundations of Algorithms. So, as promised, every class I want to present a historical figure, and today's figure is quite interesting. It's Tony Hoare, who you will have just seen up there in the intro. And he is a historical figure only as of this month. He passed away on the 5th of March. And he is responsible, he was age 92, and he was responsible for one of the most famous sorting algorithms, Quicksort, that we will talk about perhaps later this lecture or early next lecture, as well as a lot of the theory needed to prove the correctness of algorithms. And that's something that we're going to be worried about just as much as we're worried about the time complexity. And so stay tuned for a little more on that. Now, the topic of this lecture is going to be about machines. Now, we've talked a lot about the more abstract kind of stuff around algorithms, but at some point, the rubber needs to hit the road. Our algorithms need to actually run on some substrate, and in this case, these will be our physical digital computers that we've built. And here I have an image of Lynn Conway, who's one of the most prominent transgender contributors to computer science. And in particular, she was responsible for the architecture that is present in many modern computers and had the foresight many, many decades ago about the design of a very integrated kind of computer chip, which is indeed what finally made its way in about the year 2000 into the modern line of Macs that have integrated memory and compute in the same physical chip. And this is what it actually looks like at kind of at the micrometer scale, or if you zoom in a little, at the nanometer scale. This is what the memory of a computer looks like. And it's going to be important for us to understand how the physical memory is constructed, because that's going to determine a little how we design more conceptual and more abstract notions of how we access and play with that memory. So the operating system is going to be responsible for the translation between the physical circuitry and the software that we're used to writing. So the operating system is going to have access to actually send some physical signals down to the hardware level, and we want our software to not have to worry about the particular physical components inside a given computer. And so one of the major jobs of the operating system is to mediate between drivers, pieces of software that really understand the hardware at a deep level, and the software that sits a little above that, which shouldn't really have to worry about the particular details of the chip. Now, the way that most operating systems typically do this is they let us treat memory as if it were all just physically a bunch of boxes in a line. Now, we've seen the model of a bunch of boxes in a line referring to memory. Where have we seen that in C? Arrays. That was good timing, of course. So our arrays are our prototypical example of a memory model that more or less matches what the physical hardware looks like, but is still abstracted away. Because if we were to take that photo that I had up before and actually look at what's going on, it's not all just in a single line, it's a bit more three-dimensional, it might be arranged in rows, there might be multiple chips inside the computer. And we don't want to have to worry about that as programmers. You don't want to have to worry about how many RAM chips does this particular computer have and how are those RAM chips designed? Where physically do I have to send a signal in order to put some memory? Now, the operating system is also going to segment some of that memory and divide it among the different programs running on your computer. After all, you wouldn't want your top secret crypto software to be directly connected to your email client so that if someone sent an email, if that email was malicious, it could access the crypto wallet's memory. That would be a really bad thing. Likewise, the part of the operating system that controls which user is controlling which program, you wouldn't want one program from one user to be able to see the memory of a program of another user. So one of the big jobs of the operating system is to show different parts of the memory to those different processes, to those differently privileged users. And what happens if you write to a place that isn't allowed by the operating system? We get an error that many of you might have already seen or will start seeing in future. This is a segfault, which is short for a segmentation fault. Why? Well, because the operating system divides up the computer's memory into different segments, and when you touch a segment that you've not been given permission to access, you get a segmentation fault. And a fault is another way that the computer another way by which a computer calls errors. So modern operating systems will divide up memory by different numbers, and so you'll have a different address is one way of calling it that refers to a particular part of the computer's memory. And 0, despite being a perfectly legitimate number, is not a legitimate part of a computer's memory address. Instead, the operating system reserves the number 0 to mean no such address or empty or error or anything like that. And we call this a null pointer. And we'll talk about what the word pointer means in a second. But note it here as well, this is null with 2 L's, which is different from the ASCII null with 1 L. ASCII null is a blank character, and in operating systems, null with 2 L's is a 0 pointer. This is a map of the way that an operating system might divide a computer's memory. And this is pretty typical. You don't have to worry about the details of this for this class, but understanding it will help you actually do some of the more practical things that we have to do, because understanding what's going on here makes it easier to do some of the things that we necessarily have to do as programmers. So it's divided up into a number of different chunks, into a number of different segments. And let's start with one that you've all been using already without even knowing about it. This is the stack. Anytime you make a variable in C, the way that we've been used to making variables so far, that variable is getting added to the stack. And you can see that the stack is what we'd call a very high part of the computer's memory. So here, the address closest to 0 is at the bottom of the picture, and the high addresses closest to the maximum of a 32-bit integer in this case are at the top. So we can see it's a 32-bit integer because in base 16, if you count up the number of F's there are the maximum value it could hold is the same as an integer that has 32 bits. Now, the other thing that's kind of interesting that's going on here that we've already been using is that text segment down at the bottom. Now, text is really a bit of a misnomer here. This is where the actual code of your program is inside the computer's memory when you run your program. Now, that might seem a little funny for a minute. What do you mean where the code of my program is? Isn't that on the hard drive? Well, if you want to run the program that you've made, there's an additional step that we have been not talking about very well so far. So firstly, we write our code in a text file. The compiler compiles it and turns it into machine code. But then somehow we need to give that machine code to the actual circuitry of the computer if the computer is going to run it. And how do we give it to the circuitry? We take it from the hard drive, which is a physical spinning disk, or maybe now it's solid state somewhere in the computer. We take it from there and we put it into the computer's RAM, the random access memory, its working memory, where it stores things that it's currently working on. And from that RAM, it can then be fed into the central processing unit, the CPU, which is the actual circuitry that does the computations. And so part of that process of moving it from the hard drive into the computer's working memory means that it has to be assigned one of these addresses. And so the entire program is given a chunk of the computer's memory, divided into segments, and one of those segments will have the variables, and one of the segments will have the actual code instructions to then be fed to the circuitry. And that's what's happening in the text segment. Now, what happens if you accidentally try and write something to the text segment? What do you think the computer will do? You will get a segfault, a segmentation fault. This is because the text segment is now meant to be read-only. Once it's been established, once you've loaded your program code in, it shouldn't be able to be tampered with, because that might mean that someone is trying to overwrite the instructions in your program and put some malicious code in. And that's historically how a lot of early hacks were done, is people would manipulate programs that were running, try and write stuff into that text segment, and then when the computer looked for the next instructions, it would go to the text segment and read what the malicious user had put in there instead of what the programmer had put in there in the first place. So let's talk about memory a little more. Now, this is the most blank way of viewing it, which is just as an empty set of boxes. But we're going to impose the notion of an address on top of this. And it doesn't really matter for our purposes how the operating system is going to translate between the addresses that we're using and the actual physical locations. If you want to know more about that, we can go to an operating systems class in your third year. But for now, let's just assign them numbers from 0 to 6 in this case, for we have 6 boxes. And this is why an array is a collection of like objects. Because if each object is just one slot in memory, if we start trying to put in different objects of different sizes, then we're going to run into problems with our abstraction. We're not going to be able to cleanly deal with it using this idea of boxes of all the same size. So let's take a break from some of this more theoretical stuff and think about what that means in practice. So I'm going to need a volunteer. This is a really fun demo and it's not a hard one. Okay, here's concoction A. That is my variable x and this is my variable y.
There we go.
Okay, you can hand me that, or you can put it in your pocket or whatever. And that's my variable x and my variable y. Can you swap what is in each of the containers?
No, not right now.
What do you mean?
Will that overflow?
Say again, so why can't we swap our two variables?
Because it'll overflow and spill everywhere.
But in C we do this all the time, don't we? Yeah. How do we do it in C or in a programming language?
We have a temporary place where we can put it.
Okay, wait a second. Okay, so let's go through this properly. So I've got my variable, my x, my variable y, and what should we call this?
Z.
Okay, and so if I want to put whatever is in x into y, and whatever is in y into z, what's my process?
You put x into z. Oh, okay. Hope I don't spill it. There we go.
Okay, voila. And now what?
Oh, is this for me?
Yeah.
You put y into x.
Okay, let's do that. Okay.
And then you put z into y.
And we'll do this last one. Do you want to do it? Okay. And voila, we have an integer swap. So let's take a round of applause. Thank you very much. It was Zach, right? Thank you. I told you, easiest demo of the semester. Okay, and we'll put my beautiful fluorescent, over on the side. And you can go back and let's look at the code that does that really quickly, because by now this much should not be that difficult for all of you. So let's open swap 1, and we're not going to spend very long on it because it is not very difficult code. Okay, enter a value of x, scanf, enter a value of y, scanf, create a temporary variable. That's our temporary one over here. Pour x into the temp, pour y into x, and then pour whatever is in the temporary back into y. Okay, seems pretty straightforward. But now we have a bit of an issue because we remember some of the rules that C has about functions. So now let's make this into a function. Let's make this into a function. We'll return 0 on success, and then we'll call our function here swap1 xy. What have I done? Oh, I forgot to put the function prototype at the top. Okay, let's put that in. And and a mistake in what I wrote. So let's do that one more time. Run swap one. Enter value of x, 5, enter value of y, 7. After swapping, x is still 5 and y is still equal to 7. Now, if we remember from our last lecture, there's something going on that there's one word to describe. What's that word? Scope. Who said that? Good job, Tom. The answer is scope. So what has been happening is the value is x and y inside the swap function are not the same x and y that are in the main function. What has actually happened is that C has done what we call pass by value. And you can think of this just like a photocopier. So when we call the function swap1 with two variables x and y, what's happened is it actually makes a photocopy of the x and makes a photocopy of the y, gives those to the functions and says, call those photocopies whatever you like. I'm keeping my originals to myself. That's what pass by value means, because you copy the value to the new function and you're not telling the new function where to find those original glass files. It would be as if I had another set of files that belonged to that other function. And this is generally true. C functions are always going to make copies of whatever their inputs are. But this leaves us with a bit of a puzzle. After all, we actually want to do this swapping thing, and it seems kind of mean that the programming language is preventing us. But fear not, my brave travelers. The inventors of the C programming language, or the developers of the C programming language, did actually account for this, and this is going to be one of the big concepts that we'll learn today, but also one of the trickier parts of semester. And this is the notion of pointers. Now, don't worry if you don't get it at first. I will say this is one of the harder things to get your head around, so we're going to work through it a little slowly, use some of these analogies to hopefully give you some intuition about how they work. So, when you modify the input to a function, after you return from the function, unless you have modified the original copies of the variables that sat outside the function itself, the functions you've created inside the function get destroyed and nothing outside will get modified. What we can do, though, is modify outside memory through the notion of a pointer. And that's what we're going to do now. Now, what is a pointer? It's really just another variable. And like any other variable, when you pass a pointer, and we'll talk about what this means in more depth in a minute, when you give a pointer to a function, whatever that variable is, just like any other variable, a copy of it gets made, a photocopy gets made and given to that function. Now, the special thing about a pointer, though, is what's actually stored in that variable is not going to be just any other number. It'll be one of those memory addresses that we were talking about earlier. So when we had that picture of all the different segments, what we're going to copy into our function is actually a number that refers to somewhere in that big picture of segments. And then we can use that to jump directly to that address. So now, in order to actually understand this concept, we need a couple of volunteers again. Now, this demo is very similar in difficulty to the other one, so please don't be shy of coming down to the front. I would love some volunteers. So Andrew is doing his normal business one day and he decides he wants to store some variables. So he thinks, you know what? I like the number 8 a lot and I am going to put it in a variable of my choice. So we'll give you the number 8 and place it in a variable of your choice. Yeah, okay. So, Andrew, can you explain what you've just done in terms of C?
Like if this is a variable a, I like a equals to 8.
A equals 8, very good. Okay, so when we read variable a, what do we see?
We see 8.
Okay, can you do that for me? Just pull it up and show everyone.
8.
Great. Whoa, okay. But wait a minute. Put the number away for a second, yeah? Can you go to location 2 for me in the computer's memory? Just walk over to location 2.
2.
Yeah, Okay? Can you walk over to location 8?
8 here.
Okay. Now choose where you want to put your number 8 again. Remember, Andrew loves the number 8. He's going to put it in a variable.
Putting this again.
Yeah? So where have you put the number 8? At what address?
Address 8.
Whoa, wait a minute. You can put the number 8 inside the mailbox of house number 8?
Yes?
Yeah, why not? Okay, so let's do something even cooler. Take the number 8 out, and let's put the number 8 at house number 2. Okay, now I've got something new for you. This is a real trick. Okay, this is the magic star of dereferencing, and it has a dance with it, right? The way we use it is you go, woo, just like that. And the magic power that you do is, let's say we have a variable b is at number 2 over here. What the magic star of dereferencing does is, let's say we do star b. What's going to happen, now this is a multi-step process, come over here, Andrew. To use the star of dereferencing, you open the box, Open the box. Yep, take the star of dereferencing. Woo! Now we look at the number we just pulled out.
8.
Yep. And what we do is we visit the house whose number we just picked up.
House 2.
Wait, which house number did you just pick up?
This house. Oh, sorry, 8.
Picked up house number, we picked up number 8. It was in house number 2, but the number we picked up was number 8. And so now we visit number 8 and check inside its mailbox.
This one?
That's house number 8.
This one.
No, you were right. That's house number 8. So check inside the mailbox, and what do we have?
4.
Okay, pull it out and show us. Oh, that's okay. That was magic. Let's do that one more time. Okay, let's store 4 in variable A and close it up. And remember, variable A, what's its house address?
8.
8. Okay. So let's go back to house number 2. And inside house number 2, we can store the number 8. Okay, now we'll do 2 things. I'm going to take away your star of dereferencing. Okay, can you access variable B for me? Remember, variable B was at address 2. Okay, what did you pull out?
8.
That's a bit sad. Nothing special happened. Okay, put it back. Okay, and now we're going to use our magic star of dereferencing and do the same thing. Okay, access variable B with a dereference star. Okay, explain to everyone what you're doing.
I'm going to the address of 8.
So let's back up. That's correct, but let's back up a little. So when we use the dereference star, we first look at what's inside that variable, we pull it out, and instead of treating it like a normal number, we treat it like
Address?
an address. Okay. So now we have number 8. What do?
I got 4.
Yeah. Okay, let's do one more example, only this time I'm going to do it the other way around. And I have something else in here for you. Yeah. Okay, so now let's redesign our variables a little, and now this is no longer address number 2. We're going to make this address number 4, just so our demo works nicely. Okay. So I want you to visit variable A and use the magic star of dereferencing. Okay, wait a minute.
Whee!
Okay.
That will be 4.
Yeah. Okay, and what do?
Find the address 4.
Okay, let's visit house number 4.
That will be 7.
Yep, and so the answer is 7. So this is what we're going to be doing with pointers, is whenever you see the magic star of dereferencing, and that is a trademarked term for foundations of algorithms, magic star of dereferencing. You might just see it as regular dereferencing elsewhere, but we're magic here. when you see the star of dereferencing, think of this procedure where you go to the variable that's indicated by the star, you look what's inside it, and instead of treating it like any old number, you instead visit the address of that number. So just like he pulled out 4 and then went to address 4 and looked inside the box, and the final answer was 7, this is exactly what we're going to be doing in C. So can we have a huge round of applause for our 3 volunteers? Lou, Andrew, and Ziad. So I also want to give a big shout out to Jisoo Jion from the Telstra Creator Space, who taught me how to enough woodwork and metalwork to actually make our letterboxes for today's demo. So this is another representation of exactly the same thing that we've been seeing. We can create a series of variables, and in this case, let's make an array, and we're going to fill it with 5 characters and one special 0 character at the end, and this is the null byte that I was talking about, which is not actually a 0, it's like a special ASCII 0, and this is null with 1 L. So we're going to fill up our 6 slots in our array with different ASCII values. And you're going to notice something interesting here. It's a little hard to see in the particular lighting. You'll notice something interesting here, that we haven't actually separated the addresses by 1, 2, 3, 4, 5. We're instead going up by something a little different. What's happening here? Yes?
Hexadecimal.
Let's pass that back. And remind me your name again.
I'm Jay.
Jay. So what's going on here?
It's using hexadecimal.
So that's the first thing to point out, is it's using hexadecimal. So we're not counting in base 10, instead we're counting in base 16. So everyone count with me. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. That's 16 digits. What do we do after that? So for some people in the room know the answer, but just like when we run out of digits when we count in base 10, so we have 0 to 9, so that's 10 digits. When we run out of digits, what we do is we go back to that first digit again, that 1, and then we do 1, 0. So there's a 1 in the tens column and a 0's in the ones column. So what we're going to do in base 16 is the same thing. We're going to put a 1 in the 16s column and a 0 in the ones column. And so then we go 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. 1A, 1B, 1C, 1D, 1E, 1F. We've run out of digits in the ones column, so we add a 1 in the 16s column. So 2, 0, 2A, 2B, 2C, 2D, 2E, 2F, and so on and so forth. And then when we get to, let's say, 9F, now we've run out of digits for the ones column, and we need to add 1 to the 16s column. So instead of 9, we'll go to A. So A0, A1, A2, A3, all the way up to FF. And when we get to FF, we're out of digits for the ones column. We're out of digits for the 16s column. And so what we do is we add a 1 in the third place, and then we set the others to 0. So that takes us to 1, 0, 0, all the way through FFF. And so when we saw in our map of the computer's memory before that a 32-bit integer could be represented as 8 Fs, that's because each of the places was going up a subsequent power of 16 rather than a power of 10. So it allows us to write things much more compactly. So that's what we've done here. Now, another fact to note, another thing to note on our addressing is that 1 byte that you can store 1 character in, so from 0 to 255, takes 8 bits. So 8 ones and zeros, 8 switches, like we talked about early in semester. So the next address is always going to be the previous address plus 8. Now, why don't we just use bits? Why do we always use bytes inside a computer? There are 2 reasons to this. One is just historical accident. That's how we develop things. But why did we develop things that way? Why were we always using powers of 2? Why were we doing 1 byte is 8 bits? That comes down to how easy it is to actually make the physical architecture, the physical circuitry that operates on these things. And it turns out that it was simpler in a lot of cases to, or more efficient to use some of these power of 2 values and to do our addressing at the byte level rather than the bit level. So the other one, I'll give you a third reason as well. We use bytes a lot. We use chars a lot. We don't do very much work in computers, in computer science that operates just on individual bits. We do a little bit of it, and we'll talk about how to do that in, I think, like week 10. But bytes are a far more common unit of analysis, so it makes sense for us to design our computers that way. So let's peek behind the hood at what's happening, what the computer's actually doing when I put hello/0, that null byte, into the computer's memory. All I've done is actually put very small integers into those slots. Now, when I use the word integer here, I'm talking about it in the mathematical sense, not in the 32-bit integer kind of computing sense. And so I can write down the numbers that represent hello/0. And I can also list it just like that picture of the computer's memory that I did before. So instead of writing it out left to right, I can kind of write it out top to bottom this way. Oop. So just like we were doing before with our mailbox demo, we can choose how we interpret the numbers that are at any of these given locations. So we can interpret them as a character, so we can read 1 box at a time and read that as a character, or we could read 4 boxes at a time and read it like a 32-bit integer, or read 8 boxes at a time and read those boxes like we're trying to read a 64-bit integer. And the other thing we could do is read some of the boxes, if we have the right number of boxes, as actually referring to an address, just like we were doing before when we picked up the number 8. It could be just the plain number 8, or it could be location 8. And we'll talk about momentarily how to signify to the computer that we want to do an interpretation in a given way. Now, we can signify to the computer that we want to do the interpretation in a certain way, and the way we've done that thus far in class is by using types and casting, and we can do the same thing here. So in this example, you'll see that the 32-bit value stored at location 8, so if we read 4 boxes, which is equivalent to 4 bytes, which is 32 bits, which is the size of a normal integer, at least in older computers. The 32-bit value stored starting at address 8 corresponds to 00000030. Now, if we look at our picture, that 00000030 we could treat as an address. So if I look up there, what's at 00000030? Can anyone see? 10. Yeah, the number 10. So if I were to take my magic star of dereferencing, and apply it to the variable that is located at address 8 or 0x8, the outcome of that would be the number 10. Because what we do is we look at our variable that starts at 8, we see 000000, and because those are leading zeros, just like if you were to write the number 10, 010, it's still the number 10, you just cross off those zeros that mean nothing out the front. So just like we're doing that, we read the number, we see, oh, 0x30, we go to location 30, and we look at what's inside it. So, meanwhile, 30 contains the number 10, and so that's going to be our final result here. And in the words of Gollum, tricksy. Okay, let's go over that one more time again. Why is this working? It's working because addresses are a number, just like any other number. And addresses can also store numbers. So just like a street house on a regular street has a number that the house belongs to, but you can put a piece of paper inside their mailbox that also has a number on it that refers to another house in the street. So, how do we know which variable we should treat as a number and which we should treat as an address? Well, this is up to the designers of the programming language to figure out how do I give the people who write in my programming language some way of symbolically representing how they want a given number to be treated. So in this case, we're going to use two symbols. We'll use my magic star of dereferencing and my ampersand over here. And these are going to be our two tools that we'll use for pointers. Now, one of the kind of confusing things is that this symbol has multiple uses in C. It's going to be used both to indicate which things should be treated as a pointer. It's going to be used as the magic star of dereferencing, and it's also just going to be used as the multiplication symbol. And so one of the things that students often find very hard is figuring out, okay, what does this do again? And remembering that there are those three separate functions that it can perform, and remembering what is the syntax that indicates which is a very useful thing to spend a little bit of time going over, because then you'll get less confused once you've done that initial work to remember which of the use cases it is. So in this case, the 8-bit value stored at 0x20, so that's 1 byte, at address 0x20, there is a single byte which contains 0x68, and 68, or 68 in hex, is H. The 8-bit value stored at 0x2 plus size of char. How large is the char? It's 1 byte, so that'll move us how many bits along? 8 bits along. That would take us to 0x28 over there. And at 0x28, the number 0x69 is stored. You know what I should have done? 67, but was not smart enough. And so how do we tell the compiler that we want to treat these as pointers? What we do is we use this declaration that includes the star. So if I write char star A, that means treat variable A as a pointer, however large a pointer happens to be on your computer. And when someone uses the star of dereferencing at A, go to the address located inside A. And so if we are on a machine that uses pointers that are only 1 byte long, and again, this is a hypothetical, if we're on a machine that uses pointers that are only 1 byte long, and I dereference A, which has 068, then what do I do? Where do I go? We'll give it to you. What's your name?
Oh, my name's Jerry.
Jerry. So Jerry, let's say I apply the star of dereferencing to A. What do I get? So A contains the value 68. And so I apply the dereference to A. Where do I go?
You actually decoding this address.
So what I do, I look at A and I read the value inside. Now I told you it's 68, right? So where do I go?
You go to 68's box.
Yep. I go to 68's box and it is really hard to read. And so that would take us to 68's box, which has a 00 in it. This is another even more confusing example. And this is a pointer to a pointer. So a pointer could point to an integer, like we saw before, where it took us to the number 8. Thank you very much, Jerry. Or a pointer could take us to a char, a single letter. A pointer could take us to a 32-bit integer. Or a pointer could take us to a mailbox that inside it has another pointer. So imagine I went to address 4 that I had over here, and I use the star of dereferencing, and inside I see the number 8. And the number 8 is also a pointer, so I can dereference that. And then when I go to number 8, I see the number 3 or something like that. And so we can do that in our computer's memory as well. And in this class, you will, in a few occasions, see pointers to pointers, We're not going to test you very hard on them because it's conceptually a bit tricky and getting your heads around single pointers is enough, but it can be done. So the star here, in this case, is officially known as the dereferencing operator. It's just like plus, minus, division, modulo in terms of having a place in the hierarchy and operating on variables, transforming them. So dereferencing you can think of as just like visiting the mailbox. Just knowing the address is not enough to find out what's inside. So you visit the mailbox, you pick up the number inside, you visit the location it refers to, and then you pick up what's inside that box. Okay, and we do have another operator that I mentioned is critical as well, and this is our ampersand operator, also known as address of. Is that a question? Okay. Just holding it backwards. There we go. Our ampersand operator, which is also known as the address of operator. And so this, remember I had my variables A and B before, and I said, oh, well, let's call this one at address 4 and that one at address 8. How would I know what those numbers are? Normally when I use variables, I'm not like saying, okay, put A at house address number 4 in the memory and then store 8 in address number 4. No, I'm never doing that. I'm referring to them by their name. But sometimes you actually want to know where they are in the computer's memory. And so if you want that, write the ampersand followed by the name of the variable. So I had B that was at location 4. So ampersand B would be what? 4. Yeah. So this is like checking the address on top of a mailbox. At what house number is that variable located? And it gives you that address for future use so that you can then use this address to give to other people. So just like if I want to put something in your mailbox, I first have to know the address of your mailbox. You can use the ampersand operator to get that address. So for the time being, all of the variables that we're using until we get a little later in the class are going to be stored in the stack. And so they're going to have addresses that reflect this segment of the computer's memory. Now, later on, we will use some of the other segments. In particular, we will use the heap and learn how to manipulate those addresses as well. Now, one kind of caveat that I mentioned earlier in semester is that even though in this picture and in all the demos thus far, I've used addresses that are 32 bits, which is how many bytes? 4 bytes. Most modern computers now, and even most modern phones, now use 64-bit addresses. So that means that if we were to make a picture of this, the number of zeros would be far more and the number of Fs would be double as well. And this is so that we actually have more places to store things in the computer's memory. Now, we're going to pause for a second and I will give you one advanced thing which is very non-accessible. Now, inside a computer's memory, you can imagine a computer that has 32 bits worth of addresses. So 32 bits counts up to what number, again, roughly? 4 billion is the answer. And so there are 4 billion individual bits that we can talk about inside the computer's RAM, inside its working memory. So that means we can only have 4 billion bits, and if we convert that, that is about 4-ish gigabytes. Now, how much memory does an average computer have today? 8, 16, so 32, 64 in case of my computer. And so one of the reasons why we want to move to these larger size addresses is so that we can have a computer that has more boxes where we can put memory inside of it. Now, even though we in theory have room for 2 to the 64 places, 2 to the 64 boxes, a physical computer that you buy probably doesn't have enough RAM to actually use all of that. And so what the operating system is going to do is it's going to tell you that all of these spaces are available, but behind the scenes, it's going to figure out, okay, I'm going to tell the program that they can use any of the 2 to the 64 places, but whenever they ask for one of the places, I'm going to choose where in the computer's RAM that actually goes. And every program is going to see its own version of the complete address space and think it can put things anywhere. But secretly what I'm going to do is when we're talking about the physical hardware, I'm going to give them all separate chunks of the physical hardware, even if they've used the same number. So if you ask for the number 8 in your program and another program asks for the number 8, the operating system will convert it to separate places. And that's called virtual memory, a key concept that makes modern computers run, but not something that you need to worry about for the rest of this class. I just thought it would be interesting and helpful to know at this stage, because again, it can alleviate some confusion, but if that was too complicated for you, do not worry about it. So remember that C was passed by value. This means that whenever we give a function a value, we're not actually giving it the variable itself. What we're doing is photocopying that variable. But just like we can photocopy the number 8 into a function, we could photocopy the number 8 and treat it as a pointer. And so this means we're going to tell the function, hey, function, when you receive this number, treat it as an address. And when the function receives it, it can then use it to go to that location. It can still use the star of dereferencing, even though it's a photocopy. Just like on a physical piece of mail, if you were to photocopy someone's address, you can still use it to go to that place, even though the thing that you're writing on is a photocopy. So if you change it, it's not changing anything else in the world. You can interpret it instead of worrying about changing it directly. You can interpret it and say, oh, this is location 17 Main Street. If I want to change what's in 17 Main Street's mailbox, I can now do that because I know where 17 Main Street is. So now let's see a demo of actually using all of this in practice, now that we've done a lot of work trying to make it conceptually approachable. So let's look at a few key features of this. So it starts off the same with our main function until we hit the scanf, and this is actually the same, but you'll notice something interesting here. I've used the ampersand symbol in scanf, and we've actually been doing this all along. I just told you, use the ampersand to make scanf work. And the reason why we're doing this will become clear soon, but it's because what we're giving scanf is not a copy of the variable. We're actually giving scanf the address of the variable. And why would we do that? Well, we want scanf to be able to modify the variable itself and not modify the copy of the variable, the photocopy that it gets when scanf starts running. So we've got our enter x and enter y. And then we do swap, but this time, instead of giving swap a copy of the variables themselves, we're giving swap a copy of the addresses of the variables. That means that swap knows where to go in the computer's memory if it wants to find where those things actually are in the first place. So now let's look at swap. Swap is written as such. It has two integers. But wait a minute, these are not plain integers. These are integer pointers. This star might actually be more clearly written if I'd written it out this way. So this is actually the type. They're two integer pointers. And what that means is not that the size of the pointer is an integer. It means that the thing that the pointer is pointing to should be treated like an integer when you arrive. So remember that a pointer is an address, and when we get to that address, we see a number, and we have to know how to treat that number. Is that number a character? Is that number going to be an integer, in which case we need to look at the next 4 places? Or is it a pointer itself, in which case we're going to need to treat that as an address and maybe jump a second time? So in this case, what we're saying is this function takes in 2 addresses, and each of those addresses should contain an integer. Now, because an integer takes up 4 bytes, this address is just going to be the start of those 4 bytes. So it says, like, go to location 8, look at the next 4 boxes, and interpret that group of 4 boxes together as an integer. Now, of course, we're on a 64-bit machine realistically here, so our pointer is going to be 8 boxes and our integer is going to be 8 boxes. But in theory, those two could be different things. You could have a machine where a pointer is 8 boxes and an integer is 4 boxes. So now let's look at what we're doing very carefully here. This is the same as our swapping example before, except this time, instead of copying the actual values in, now, this is almost the same as before, except we're doing something a little more subtle here. So the first thing we do is we take xp, whatever variable that was, remember it's an address, and we use the magic star of dereferencing, woo! And so what this does is it figures out, okay, what address is stored inside xp. Let's now visit that address and take whatever that value is and put it inside our temporary container. Okay, so our temporary container is now storing whatever used to be at the address pointed to by xp. Now, figure out what particular thing is located in the address pointed to by yp. Put whatever is pointed to by yp inside of the address pointed to by xp. And so these are two kind of subtly different uses of the dereference operator. This one is an access to the pointed to address, and this combination here is a store to that address. So that means go to the mailbox that is pointed to, so if I had my mailbox here and it had the number 8, go to location number 8 and store whatever is on the other side of the equal sign inside mailbox number 8. And so this particular line can be kind of tricky to understand because we've got two different dereferences going on. So the way I would think about it is really slowing down, breaking it down, and first ask, okay, what does this side do? And then what does that side do? So this side is figuring out what is inside the mailbox at address yp, pointed to by yp. And then this says, go to the location pointed to by xp and store whatever you just found there. And then our last step says, go to the address stored in yp and store whatever was in our temporary one. Now this example I anticipate might not actually have sunk in through what I just said. This might actually take some drawing out some pictures. And so I would encourage you over the next week to go through this particular example very carefully and very slowly, because if you can get this one, the rest of pointers will become much easier. Now, of course, we do want to run it to actually know that it works. So, oh, I'm not in the right directory. Enter a value of x, enter a value of y, and after swapping back in the main function, I've successfully managed to change the variables in main. So I'm not changing the copies that have been photocopied into swap. I've actually changed the values inside main. And the way I did that was by photocopying not what x and y were. I photocopied their addresses and I gave those addresses to the swap function. And then swap could say, okay, I don't know what's inside x and y right now, but I know where to find them in the computer's memory. And so what I can do is I'll look at the addresses that I have photocopied here, and then I'll go over here every time I need to actually do operations with them, because my photocopies tell me how to get from here to over there. The big takeaway here is that if you know where in a computer's memory, or where in your program's memory, I should say, because we learned a little about virtual memory, if you know where a variable is in memory and you have permission from the operating system, you can change it. What do you think happens if you don't have permission from the operating system? Segfaults! So our pointer variables, just like any other variable, can be set to 0. And 0 is the special value that we reserve just by convention to be null. Null again with 2 L's as opposed to with 1 L. And if you dereference a null pointer, what do we get? Segfault. Okay. It's a trap. The star symbol is used in multiple different ways. Again, the ones we talked about as the multiplication operator, as the dereferencing operator, and when you're setting up a pointer variable initially, as the type declaration for a pointer variable. So think about these three carefully and you'll be right. Hello again, everyone. We're going to spend a couple of minutes going through some very quick code demos around pointers just to give you a little more familiarity with the use of them in practice before we'll move back to some conceptual material again. So here you can see I've declared a number of different types of variables, and the goal here is just to notice that they give us kind of different addresses when we declare our variables on the stack, as opposed to a static integer, which is actually going to be stored somewhere else in the computer's memory. So let's give this a run and actually see what the result is. So you can see our three variables on the stack are integers that are going to be separated by exactly the size of an integer. So in this case, they're going to be separated by 4 bytes. 1c plus 4 is 20, 20 plus 4 is 24. But our w integer, which is a static integer, appears somewhere entirely different in the computer's memory. If we go back to our picture over here and we carefully look at the text on the downloaded slides, you'll see that that's actually the data or the BSS section where static variables are stored. Who has an idea why we might store static variables in a different place to where we store regular variables inside a function? What happens when, okay, KJ, you haven't spoken in a while. I was hoping you'd put up your hand. KJ, what happens when a function ends?
So for this function, the three variables that were initialized within the function would sort of get destroyed, like be able to reference back to them.
And what's the point of a static integer?
You can reference back to it within the same function, so it doesn't just immediately get destroyed after you run it once.
Yeah, so we want it to stick around. Even if we call the function a second time, we want that static variable to still have existed. And so by putting it in a separate part of the memory, this ensures that when we clean up that part of the stack, when we reuse it for other things, that static variable still sticks around. And so that's why we put it in a different segment. Okay, now we have another one that's starting to get a little more sophisticated. And this is pointer2.c. So there are a couple of features in here. One of them is actually pretty averse to my personal coding style, which is doing multiple declarations on the same line and separating them by a comma. C does allow you to do this, but it's easy to get confused quickly by what things are possible and what things are not. So in this case, all the comma is doing is it's saying we're still making another integer, but this one is an integer pointer. So it's a pointer that points to an integer, and we're calling it pi. Likewise, we're going to create a pointer to a double called PD, as well as a double itself that's going to be x. Oh, one other thing I should show you in pointer 1 is that we're now using the p flag, which is to print an address. That's the format specifier, and we're saying show the entire 16 characters that it takes to show a 64-bit address. Okay, back to our pointer 2. So the first thing we're going to do is we will print n, which is just our number 1, 2, 3, and then we will print x, which is our double. Next thing we're going to do is we are going to take the address of the two variables we've just created using the ampersand operator, using the address of operator, and see what the address of those variables are. We'll look at those first two parts of the code so far. So as expected, n is 1, 2, 3, x is 456.789. Then when we take the address of them and then subsequently dereference the address, what we're doing is we're saying, essentially, in these two variables, pi and pn, store the addresses of those variables. And when we dereference them, we're saying now, take those addresses that you've just put elsewhere and figure out what's at those addresses. So it's kind of like the inverse operation of what we've just done. So we get back 1, 2, 3, and then 456.789. The next thing we do is we're going to use the dereference operator on both sides here. So figure out what is at the address pointed to by PI, add 1 to it, and then go to the address to which PI refers and store whatever you just got at it. So this is really just the same as writing n equals n plus 1 in a fancy way. Likewise, on the other side here, this says, figure out what is at the address to pointed to by PI, figure out what's at the address pointed to by PD, divide one by the other, and then store the outcome in PD. And so if we look at what happens here, PI has changed because even though PI and n are separate variables, PI is telling the program to go to the address of n and modify it. So it's saying go to wherever n is stored, maybe n is stored at address 8, and do your operations there. So even though the thing that is inside PI itself is a number that's an address, whenever we use the star operator, we're saying, look at the address you have. Instead of like adding 1 to that address, I want you to go to that address and add 1 to the thing that you find there. And that's what's happening here. Then we'll do one more demo. So here's our read num example again. We've already seen how to read in values a few times, and now we're going to do it again just with pointers. So let's look at the read num function. We're going to set bounds on the numbers we want to accept, and we're going to take in a pointer. And the reason we're taking in a pointer here is so that we can return the number that was within the correct bounds back to the main function. But instead of just returning it, we actually want to modify the variable that the main function originally had, just like scanf did. So just like scanf takes, just like when you run scanf, you give it the address of the variable you want to modify, of the place that you want things to end up. That's what this function is doing here. We are giving read num the address of a mailbox that we have set aside to contain the integer. And now what we want to do is we want to write a function that will take the address of that mailbox that we've put aside and fill it up appropriately. So enter a number between low and high, go in a loop, and check when the user has entered something that is valid, go to the address that the function was given and put that value inside of it, and then return read OK. If not, print an error message and continue the loop. GCC readnum.c read num. Enter a number between negative 100 and 100 inclusive, 176. That's not right. 180, negative 200, still not happy. Okay, try again. 5. Value equals 5. And let's look. Value is actually a variable that belonged in main. So even though read num has ended, and even though we've been returning either read OK or read error, read OK was 0, we still somehow managed to get what the user had typed in back to the main function. And so this is really a key message here, is that pointers are going to allow for more interaction between the calling function and the calling function scope, and between the scope of the function that the outer one called. So it allows us to modify things back in that outer scope without using global variables. Now, why would we not just want to have like a list of 100 global variables at the top of our program?
Make it hard to read.
Not only is it hard to read, but global variables create a bit of a danger point. Let's pass it over here. And what was your name?
Owen.
Owen.
It would also be like a waste of memory as well to declare all the variables at the start instead of within like a local scope.
Yeah, so if we declare all variables, but they're only needed in certain chunks of the program, that takes away our ability to just have those variables exist for a certain period of time. Because in this case, it's our value is inside the main function, so it's going to exist the whole time anyway. But let's imagine this is, instead of the main function, it's subroutine 3. we will still want to be able to destroy value when subroutine 3 ends. We just don't want it to be destroyed as soon as read num ends. So that's another reason. And on top of that, it becomes very difficult for programmers to think about which parts of the program are impacting which other parts if every part of the program can change every other part of the program. And so this is a callback to abstraction, one of the key organizing concepts of the class, which is that in order to organize computers effectively, both from hardware design and from software design and from operating system design, it's important for us to set conceptual barriers, to put limits on ourselves to organize our thoughts in ways that actually make it easy to produce readable programs, programs of which we can prove the correctness, and programs of which we can clearly understand the runtime. To wrap up for today, I only have a few things left for us. One thing that I think is important to go home and do is actually to practice this kind of idea of having different functions which have variables that might belong to them, but which are modified by other functions. So not just using the return keyword as a way of passing information between functions, but also using pointers. So here are a couple of examples of ways that you could practice this at home. So write a function that reads integers until it obtains one in the specified range and stores it in the third argument. The return value should indicate success or failure. Just like the read num we did, try and replicate that yourself. Here's another one. Write a function that orders its 3 inter arguments from smallest to largest by swapping its values. And now in particular, I think this one is useful because all the sorting stuff that we've done so far and that we're going to go back to in a minute is going to actually use pointers for implementation to do the swapping. So by practicing this exercise, you'll get yourself to a point where you can easily write the actual sorting code yourself. Now, I mentioned a little bit about scanf before, and the read num demo that we've just done is a pretty good prototype for what's happening inside scanf. However, the real scanf, and also the real printf, but the real scanf is very, very complicated. Now, I would encourage you to go look at it just to see what it looks like. But it is beyond the complexity that I think is reasonable to approach for foundations of algorithms. But the key interesting point here is understanding now why we're giving it the ampersand operator. It's because what we want scanf to do is to collect from the user a value, and not just collect it and then when scanf ends for that value to go away. We want it to be able to be placed in a variable that's been set aside by the calling function. Now, one of the nice things about scanf is you can read in multiple things at once. And this tells us why the return keyword wouldn't be quite enough on its own, because return can only return one thing. So if our scanf is going to return multiple things, pointers is probably the best way to do that. And with all of that, we have now finished all of chapters 1 to 6. We're going to do a little bit more of a discussion next week on some of the swapping and some of our algorithm stuff. But I will leave you today with a message from one of my favorite friends who has some very strong views on C. Thank you very much, and congratulations on completing the first chunk of semester.